Understanding the PF curve and component failures. In this video, we will discuss the PF curve and its relationship to failure prediction. The PF curve is one of the key tools used in reliability-centered maintenance, or RCM. When combined with condition monitoring techniques, it significantly enhances the effectiveness of maintenance decision-making and asset management. RCM uses the potential failure PF curve as a crucial tool to predict potential failures and determine appropriate maintenance strategies. The PF curve helps analyze the relationship between different failure modes and their consequences over time. This curve is a graphical representation, with the x-axis representing time and the y-axis showing the consequences or severity of failure. The PF curve helps plot the likelihood or probability of failure against its impact. In the RCM process, the PF curve is constructed by identifying various failure modes. Each mode is then evaluated based on its likelihood of occurrence and the consequences it could have on safety, the environment, production, or cost. This evaluation is based on expert judgment, historical data, maintenance records, and industry experience. To assess the likelihood of failure, several factors are considered, such as the age of equipment, maintenance history, operating conditions, and whether any failure indicators are present. The consequences of failure might include safety hazards, environmental damage, production downtime, repair costs, or reputational risk. By plotting the likelihood of failure against its consequences, the PF curve provides a clear visual representation of the risks associated with each failure mode. This enables organizations to prioritize maintenance actions and select the most suitable strategies based on the criticality and impact of potential failures. The PF curve also helps identify the optimal balance between preventive and corrective maintenance strategies. It aids in making informed decisions about maintenance intervals, inspection frequencies, and resource allocation, depending on the criticality of failure modes. The PF curve represents the typical failure lifecycle of a machine component, such as a bearing. The curve begins with the introduction of a defect, or D, marking the start of the component's deterioration. As the bearing continues to degrade, it reaches the point of potential failure, or P, where the issue can be detected through inspections or condition monitoring. If left unaddressed, the bearing will continue to deteriorate until it reaches functional failure, or F, at which point the component can no longer perform its intended function and the machine ceases to operate. Main elements of the PF curve: defect D, the initial introduction of a defect. Potential failure P, the point where the failure becomes detectable through inspections or monitoring. Functional failure F, the point where the component stops working entirely, leading to machine shutdown. Potential failure PF interval, the period between detecting a potential failure and the occurrence of functional failure. The PF curve illustrates the failure life cycle of a machine. It starts with the introduction of a defect, or D, which, if left unchecked, eventually leads to functional failure, or F. The PF curve is divided into three main zones: preventative, predictive, and run to failure. In the preventative and predictive zones, measures can be taken to prevent a potential failure, known as P, from occurring. However, in the run to failure zone, also called the PF interval, the probability of failure increases exponentially. If no action is taken in this zone, the potential failure, P, escalates to a functional failure, F, resulting in potential damage to machinery, products, or personnel. The safe zone, or preventative zone, is where failure modes have a low likelihood and minimal consequences. These failure modes may not require specific proactive maintenance but can be monitored during routine inspections. The proactive zone, or predictive zone, is where failure modes have a moderate likelihood but can lead to significant consequences. Here, proactive maintenance strategies, such as preventative maintenance or condition-based monitoring, help mitigate or prevent failure. Lastly, the reactive zone, or run-to-failure zone, is where failure modes have a high likelihood and severe consequences. In this zone, reactive strategies like corrective or breakdown maintenance are employed to address these failures immediately. In the reactive zone, or run-to-failure of the PF curve, the machine is already on the path toward functional failure. At this stage, an operator can rely on their five senses to detect physical signs that a component, like a bearing, is nearing failure. Using hearing, an operator might notice unusual noises, such as grinding, squealing, or knocking, which often indicate excessive wear, misalignment, or internal damage. Increased vibration or erratic sounds are clear signs that a component is close to failing. Through sight, visual inspections may reveal physical abnormalities, such as oil leaks, cracks, discoloration from overheating, or visible wear on parts. Excessive vibrations or abnormal movement in connected components can also be indicators of a potential failure. With touch, an operator may feel excessive heat when physically inspecting the machine, signaling overheating or increased friction. Abnormal vibrations or looseness, detected by lightly placing a hand on the machine, can indicate imbalances or internal wear. Smell can also provide important clues. The odor of burning oil, rubber, or other materials might suggest overheating, improper lubrication, or that the machine is running under stress and approaching functional failure. And while taste isn't directly involved, airborne particles or fumes from burning components can create a distinct taste sensation in the mouth, indirectly warning the operator of impending failure. By tuning into these sensory cues in the reactive zone, operators can detect the early signs of functional failure and take action before a complete breakdown occurs. Maintenance technicians receive specialized training in diagnostic testing, equipping them with the skills and tools to prevent components from entering the PF interval by identifying potential failures, P, in the proactive zone, predictive of the PF curve. This expertise enables technicians to detect early signs of wear or defects before they progress to a point where failure is inevitable. Here's how specialized training benefits each diagnostic area. In vibration analysis, technicians are trained to use equipment that monitors the condition of rotating components such as bearings, motors, and pumps. By analyzing the frequency and amplitude of vibrations, they can detect early signs of misalignment, unbalance, or bearing wear. This allows corrective action to be taken before potential failures develop. Thermography, or infrared inspection, is another key area of training. Through the use of infrared cameras, technicians can detect abnormal heat patterns that indicate electrical faults, friction, or improper lubrication. By identifying these issues early, they can prevent components from overheating and failing. Ultrasonic testing training allows technicians to detect high-frequency sounds beyond human hearing. These sounds can reveal problems such as steam or gas leaks, electrical arcing, and internal bearing defects. Detecting these issues early ensures they are addressed before further degradation occurs. Oil and lubrication analysis is another critical skill. Technicians are trained to assess the condition of lubricants and detect contaminants or improper lubrication through methods like spectrometry and particle counting. This allows them to identify early signs of wear and replace or replenish lubricants before serious damage occurs. In motor current analysis, technicians monitor electrical equipment for changes in the motor's electrical signature. Deviations from the normal current pattern can signal internal issues such as winding faults or rotor damage. Identifying these problems early enables corrective action before the motor fails. Non-destructive testing, NDT, techniques such as eddy current testing or magnetic particle inspection allow technicians to inspect metal components for internal defects, cracks, or weaknesses without damaging the parts. This training helps them spot potential failures before they lead to costly breakdowns. Finally, condition monitoring systems, CMS, training enables technicians to integrate multiple data points, such as vibration, temperature, and pressure, to monitor the health of critical equipment in real time. This proactive approach helps detect warning signs before components enter the PF interval, allowing for predictive maintenance rather than reactive repairs. By applying these diagnostic techniques and tools, maintenance technicians can identify and address issues proactively long before they become detectable failures within the PF interval.